Imagine the engine has just stopped. You're 8 minutes out from Earth, bound for Mars, and that was the whole burn. There will not be another one that matters for 259 days. So you look out, and Mars is not in front of you. It is off to one side, a small orange point nowhere near the direction you're travelling. Here is what nobody prints under the diagram. You're not going to Mars. Nothing has ever gone to a planet. You're falling around the Sun on a wider, slower loop, along a path 600 million kilometres long, to close a gap that at its narrowest is 55 million. The door you left through opens for 2 weeks every 26 months, and Mercury, not Venus, is the nearest planet to Earth, and it costs more to reach than Saturn. The number you were given was never the distance. Get cozy. If you are the kind of person who enjoys watching a simple fact turn out to have 4 flaws underneath it, a slow like and subscribe helps this channel find more minds like yours. Because by the end of tonight you will know the real answer, and it is not a number of kilometres. Now, let's slowly settle in. Somewhere in your memory there is a picture of the solar system, and it is wrong in a way nobody ever told you about. You know the one. 8 circles in a neat row sitting on a black field, each one a little further from a bright yellow disk on the left-hand side. Mercury, small and grey, Venus, pale, Earth, blue and slightly larger than it should be, Mars, rust-coloured. Then a gap, and Jupiter with its bands and its red spot, Saturn tilted so you can see the rings, and finally the 2 blue-green ones at the end that most people struggle to tell apart. Underneath each planet, a number. That is the part we're going to talk about tonight, because those numbers are the most quietly misleading pieces of information in the whole of popular science, and almost everyone who has ever read them has read them wrong. The numbers themselves are correct. That is what makes this so strange. Mercury, 58 million kilometres. Venus, 108 million. Earth, 150 million. Mars, 228 million. Jupiter, 778 million. Saturn, 1.5 billion. Uranus, 2.87 billion. Neptune, 4.5 billion. Every one of those figures is accurate to within a fraction of a percent. Astronomers have known them for centuries, and the modern versions are pinned down to a precision that would have seemed absurd to the people who first measured them. Nobody is hiding anything. Nobody has made an error. It is worth pausing on how well established these figures actually are, because it matters for everything that follows. Astronomers stopped measuring the basic ruler of the solar system decades ago and simply fixed it by agreement. Since 2012, one astronomical unit, the standard yardstick, roughly the Earth's distance from the Sun, has been defined as exactly 149,597,870.7 kilometres, not measured, defined. The measurement had become more precise than the definition it was serving, so they promoted the number to a constant and moved on. Light crosses that distance in 8 minutes and 19 seconds. Everything else in this video is going to be built on that one unit, and there is no version of the story in which it turns out to be smaller than we thought. The problem is what those numbers are describing, which is not what you think it is. Each of those figures is something called a semi-major axis. It is the average size of that planet's own orbit around the Sun. It describes a relationship between the planet and the star it circles, and nothing else. It is a fact about a loop, not a fact about a gap. When the diagram writes 228 million kilometres under a picture of Mars, it is telling you how big Mars's own path around the Sun is. It is not telling you how far Mars is from you, and it never was. But that is exactly how everybody reads it. Ask almost anyone how far away Mars is, and you will get a version of 228 million kilometres, because that is the number under the picture, and there is only one number under the picture. It arrives already shaped like an answer, and the moment you accept it as an answer, you have made a mistake that the diagram politely invited you to make, and that mistake is going to sit underneath everything else you believe about the solar system. Here is the plainest way to say it. Mars has never been 228 million kilometres from the Earth, not on any single day of your life, not on the day you were born, not on the day you first learned the number, not today. It has been 55 million kilometres away. It has been 401 million kilometres away. It has spent time at almost every value in between, but the specific number printed under its picture in every classroom you ever sat in describes something that is not the distance between you and Mars, and could not be, because that distance is not the kind of thing a single number can hold. There is a second thing hiding in that same sentence, and it is going to matter later. The word average is doing more than one job. When someone says the average distance to Mars, they might mean the average size of Mars's orbit, which is the semi-major axis. They might mean the midpoint between its closest and furthest approach to us. Or they might mean the genuine time average separation, the number you would get if you measured the gap every single day for a few thousand years and divided by the number of days. Those are three different quantities. They are all called the average distance, and the difference between the last two, for Mars alone, is about 25 million kilometres, roughly 65 times the distance from here to the Moon, hidden inside one ordinary English word that nobody thinks to question. I want to be careful here, because this could easily sound like a technicality, a pedantic correction, the sort of thing where someone points out that you have been using a word slightly imprecisely, and you nod and move on and nothing changes. It is not that. This is the first crack in something much larger, and once the crack opens, the whole structure behind it starts to come apart in a very specific and very unsettling order. Because if the distance to a planet is not a fixed number, then almost everything that gets built on top of that number is also suspect. The idea that you could rank the planets by how near they are to us turns out to be unstable, and the planet you have always been told is our closest neighbour is, when you do the arithmetic properly, not our closest neighbour at all. The idea that a spacecraft crosses the gap between two worlds turns out to be false in a way that is genuinely difficult to picture, because no spacecraft in the history of the species has ever crossed a gap. Every single one of them did something else entirely. The idea that closer means easier turns out to be backwards for some destinations, so that reaching the planet nearest to us on average costs more than twice as much as reaching one nearly 4 times further out. And the idea that these are distances at all, distances in the ordinary human sense, the sense in which a place is somewhere you could conceivably go, starts to look like the most generous assumption of the whole set. So here is the question I want to hold in front of us for the next couple of hours, and I want to be honest that I am not going to answer it until the very end. How far away are the planets, really? Not the number under the picture, the real answer, the one that accounts for everything the picture leaves out. And I am telling you now, before we start, that the real answer is far worse than the number you were given. Not slightly worse. Not worse in a way that requires a correction factor. Worse in 4 separate directions at once, each one of which is more difficult than the last, and the fourth of which has no solution and never will. I will name the 4 now without explaining any of them, so you know the shape of where we're going. The first is that the distance will not hold still. There is no number, because the number is a function of the date. The second is that the path is not the gap. The distance you must travel to reach a planet is not the distance between you and that planet, and the 2 figures can differ by a factor of 10 or more. The third is that the real cost of a destination is not measured in kilometres at all. It is measured in a completely different unit, and when you switch to that unit, the entire map rearranges itself, and some of the near things become far and some of the far things become near. And the fourth is time, which is where the honest answer lives, and where the number under the picture becomes not just inaccurate but almost cruel in its tidiness. By the end of tonight you will know exactly how much worse it is, in each of those 4 directions, and you will have a specific answer to give the next time someone asks you how far away Mars is. It will not be a number of kilometres, I will say that much. But before any of the 4, there is something else wrong with that picture in your memory, and it has nothing to do with the numbers. It has to do with the drawing itself. Because it is not just that the labels are the wrong kind of information, the arrangement is wrong too. Those 8 circles in a neat row, spaced out across the page in a pleasing rhythm, roughly the same distance apart with a slightly bigger gap after Mars. That arrangement does not resemble the solar system in any respect. Not approximately, not as a simplification. The relationship between the spacing on that page and the spacing in reality is not a matter of degree. It is a different shape, and there is a reason no textbook has ever printed an accurate one, which we will get to, and the reason is not laziness or carelessness. It is that an accurate drawing of the solar system cannot be made on paper. It cannot be made in a book, or on a poster, or on a classroom wall. The thing you would need in order to draw it honestly is not a bigger sheet, it is a dry lake bed. So let us start there. Not with how far the planets are, but with why nobody has ever managed to show you. Every diagram of the solar system you have ever seen has been compressed in one direction, by a factor of thousands, not stretched, not simplified, compressed radially along the line that runs outward from the Sun. And the compression is not applied evenly, which is the part that does the real damage. The inner planets are drawn roughly right relative to each other, and then the outer ones are hauled inward, sometimes by enormous factors, so that all 8 of them can appear on the same rectangle at the same time. The result is a picture in which the solar system looks like a row of houses on a street. In reality, it is nothing of the kind. The reason is simple and unavoidable. If you draw the solar system honestly, 7 of the 8 planets are not on the page. They are off the edge, in the margin, in the next room, down the corridor. There is no arrangement of an honest scale and a printable rectangle that puts Neptune and Mercury in the same frame with anything visible in between, so the diagram cheats, because the alternative is a diagram with 1 dot on it. And because that cheat has been made in every classroom, every textbook, every planetarium lobby, and every science documentary for over a century, the compressed version is the version that lives in everybody's head, including, until you consciously override it, yours. Let me show you what an honest one looks like, not describe it. Build it, and then walk it. Take a beach ball, a large one about 60 centimeters across, big enough that you have to use both arms. Set it down on the ground in front of you. That is the Sun. At that size, the scale of your model is roughly 1 to 2.3 billion, which means every centimeter in your model stands for about 23,000 kilometers of real space. Now start walking. You walk 25 meters, and you stop, and you put down a poppy seed. That is Mercury. You keep going. At 42 meters, you set down a peppercorn for Venus. At 65 meters, a comfortable walk, the length of a decent garden, far enough that the beach ball behind you has stopped looking like something you could touch. You place a small blue bead 5.5 millimeters across. That is the Earth. Everything that has ever happened to anyone on a bead the size of a grain of rice 65 meters from a beach ball. The Moon, on this scale, sits about 17 centimeters from that bead, and the entire orbit of the Moon around the Earth, the full extent of everywhere human beings have physically travelled in the history of the species, would fit comfortably inside a dinner plate. You keep walking. At 98 meters you set down Mars, a grain smaller than the Earth bead, about 2.9 millimeters, and then nothing happens for a very long time. You walk past 100 meters, past 150, past 200. There is nothing to put down. You're crossing the asteroid belt now, and there is nothing to represent because on this scale, the entire belt is dust you could not see if it were there. You keep walking. 250 meters, 300, and at 336 meters you finally stop and place a ball 60 millimeters across, about the size of a plum. That is Jupiter, the largest planet in the solar system, and you're now 1/3 of a kilometer from a beach ball that you can barely make out. Saturn is at 618 meters, Uranus is at 1,239, and Neptune, the last planet, the outermost world of the 8, is 1,938 meters from where you started. Nearly 2 kilometers, a 25-minute walk at a steady pace from the Sun to the edge of the planets, with the entire inner solar system contained in the first 100 meters of it, and almost nothing in the remaining 1900. And if you wanted to include the nearest star on the same model, you would need to keep walking for 17,000 kilometers. That is not an error. On a scale where the Sun is a beach ball and Neptune is 2 kilometers away, Proxima Centauri is roughly the flight distance from London to Sydney. There is a second dishonesty layered on top of the spacing, and it is easier to spot once you have walked the model. On the diagram, the planets are drawn large enough to see. They have to be, or the picture would be pointless, but that means the ratio between planet size and planet spacing on the page is off by something on the order of 1,000. In the model you just walked, Jupiter is a plum, and its nearest neighbour is 280 meters away. On the page, Jupiter is 2 centimeters across and its neighbour is 4 centimeters away. The diagram does not just squeeze the distances, it inflates the worlds until the emptiness between them disappears, and emptiness is the actual subject. And there is a third thing the walk gives you that no diagram can. At each stop, turn around and look back at the beach ball. From the Earth bead at 65 meters, it is a bright disk you could cover with a fingertip. From Jupiter, at 336 meters, it is a small bright spot. From Neptune, nearly 2 kilometers out, it is barely a disk at all, and the light falling on it is about 1/900th of what falls on Earth, because brightness drops with the square of distance. Noon on Neptune is roughly as bright as a well-lit room at dusk. The compression on the page does not only hide how far apart the planets are, it hides the fact that most of the solar system is not really lit. That is the honest picture. That is the one nobody has ever drawn for you, and now you can see why. 2 groups of people have actually built this thing at full size, and both of them are worth knowing about because they turn the abstraction into something you can visit. The first is the Sweden solar system, which is the largest permanent scale model of the solar system in the world. It runs at 1 to 20 million. The Sun is the Ericsson globe in Stockholm, a spherical building 110 meters across, which on that scale is exactly right. Mercury is 950 meters from it. Earth is 7.6 kilometers away, sitting in the Museum of Natural History, and Neptune is not in Stockholm at all. Neptune is in Söderhamn, 229 kilometers up the coast. To walk the Swedish model from the Sun to Neptune, at a steady pace, would take you about 6 weeks. The second is a film. In 2015, 2 men called Wiley Overstreet and Alex Gorosh decided to build a scale model of the solar system with a 2-scale Earth, and to do it properly, with orbits marked out on the ground. They worked out that if the Earth were the size of a marble, the model would need to be about 7 miles across, around 11 kilometers. There is nowhere in an ordinary landscape to put that. So they drove out to the Black Rock Desert in Nevada, to a dry lake bed, and spent 36 hours laying it out with the headlights of their cars tracing the orbits in long exposures. 7 miles of empty ground to hold a solar system whose largest object was the size of a beach ball, and whose Earth was a marble. That is what the honest drawing costs, not a bigger sheet of paper, a dry lake bed and a day and a half. And when it was finished, the thing they had built was almost entirely empty ground, which is the only accurate portrait of the solar system anyone has ever managed to make. I want to sit with what this does to the picture in your memory, because the correction is not the one people usually make. The usual correction is emotional. People say, space is bigger than you can imagine, and then everyone nods, and nothing actually changes in the mental image. That is not what I am saying. I am saying something narrower and more concrete. The picture in your head is not a low-resolution version of the real solar system. It is a picture of a different arrangement, one in which 8 worlds sit in a row at comparable intervals, close enough that a journey between neighbours is a reasonable idea. And that arrangement has been quietly doing your thinking for you every time you have wondered how hard it would be to go somewhere. Here is the thing that makes it worse rather than merely surprising. Every single number I just used was one of the tidy average textbook figures. I built that entire 2-kilometre walk out of semi-major axes, which means the walk I just took you on is not the honest model either. It is the best case. It is the version where every planet stands politely at its average distance and waits. They do not wait. Not one of them holds still, not for a day, and the moment you account for that, the distances stop being long and start being something else entirely. So the first of the 4 begins here. There is no number. Let me show you why. The first of the 4 is the simplest to state and the hardest to hold in your head. There is no distance to Mars. There is only a distance to Mars today. The reason is obvious once you say it out loud, and almost nobody says it out loud. Both planets are moving. Earth is going around the Sun at 29.78 kilometers per second and takes 365 days to come back to where it started. Mars is going around at 24.07 kilometers per second and takes 687 days. 2 objects on 2 different circles moving at 2 different speeds in the same plane. The gap between them is not a property of either one. It is a property of the moment. And that gap does not vary a little, it varies enormously. At its closest, in theory, Mars can come within about 54.6 million kilometers of the Earth. At its furthest, when Mars is on the opposite side of the Sun from us, the separation stretches to about 401 million kilometers. That is a swing of more than a factor of 7. Between the best day and the worst day, the distance to Mars changes by 346 million kilometers, which is more than twice the distance from here to the Sun, appearing and disappearing on a cycle forever. Put it in terms you can feel. A radio signal to Mars at its closest takes 3 minutes, at its furthest 22 minutes. Same planet, same solar system. The only thing that has changed is the date. The record is worth knowing precisely because it is one of the few numbers in this story that has a timestamp. The closest Mars has come to the Earth in recorded history was on the 27th of August, 2003 at 9:51 in the morning Universal Time. The separation measured centre to centre, was 55,758,006 kilometres. That approach was the closest in roughly 59,619 years, which means the last time Mars was that close there were no cities, no agriculture, no writing, and the next time it will be closer is the 28th of August, 2287, 261 years from now. Why so rare? Because a really close approach requires two coincidences at once. Mars has to be at opposition, which means Earth is directly between it and the Sun. That happens every 26 months, reliably. But Mars's orbit is noticeably elliptical. Its eccentricity is about 0.093, so Mars's own distance from the Sun swings between roughly 207 and 249 million kilometres over its year. For a record approach, you need the opposition to happen at the same time Mars is near the closest point of its own orbit. And because the orientation of Mars's ellipse slowly rotates over tens of thousands of years, the alignment of those two cycles drifts. The good years cluster, and then they stop, and then they come back after a very long time. The practical consequence is that oppositions are not equal. In 2003, Mars came within 56 million kilometres. In other years, an opposition puts it at 101 million. Both are Mars at its closest for that cycle. One is nearly twice the other, and it is not only the gap between planets that refuses to hold still, the planets do not even hold a fixed distance from the Sun. Mercury has the most eccentric orbit of the 8, at about 0.206, which means its own distance from the Sun swings between roughly 46 and 70 million kilometres over an 88-day year. Mercury is 50% further from the Sun at one end of its year than at the other. The number under its picture on the diagram, 58 million kilometres, is not a place Mercury sits. It is the average of a continuous slide between two very different situations, and Mercury never actually occupies it for longer than an instant twice per orbit. The outer planets take this to an extreme that is difficult to absorb. Neptune's year is 164.8 Earth years long. It was discovered in 1846, and it completed its first full orbit since discovery in 2011. One lap. In the entire history of the science that knows it exists, Neptune has gone around the Sun once. Everything we have ever observed about that planet, every measurement, every image, every calculation, has been taken during a single Neptunian year, which is like trying to characterize a season from one afternoon. Uranus is not much better at 84 years. Saturn takes 29.4, Jupiter 11.86. There is a temptation to conclude from all this variability that the numbers are soft, and I want to close that door firmly because the opposite is true. Modern planetary ephemerides, the mathematical models that predict where every planet will be at any moment, are accurate to the level of meters to tens of meters for the inner planets. We know where Mars is going to be with a precision finer than the length of the spacecraft we send there. The distance is not uncertain, it is simply not constant. Those are completely different things, and confusing them is the mistake that lets people talk themselves into believing the whole subject is guesswork. It is one of the most precisely known systems in all of science, and it will still not give you a single number. Now go back to the word average, because this is where it starts doing real damage. There are 3 numbers in circulation, and all 3 are called the average distance to Mars, and they are not the same number. The first is 228 million kilometres. That is the semi-major axis, the average size of Mars's own orbit. It is a fact about Mars and the Sun, and it should never appear in a sentence about how far away Mars is from us. But it does, constantly, because it is the number on the diagram. The second is about 227.8 million kilometres. That is the midpoint between 54.6 and 401. It happens to land almost exactly on the semi-major axis figure, which is a coincidence of geometry that has done more to entrench the confusion than anything else. And it is not really an average of anything. It is the centre of a range. It is the number halfway between the best case and the worst case, which is a different concept from the typical case. The third is the one almost nobody quotes, and it is the only one that answers the question people are actually asking. If you measured the gap between Earth and Mars every single day for a few thousand years and took the mean, you would get about 1.69 astronomical units, roughly 253 million kilometres. Look at the gap between the second figure and the third, 25 million kilometres. That is about 65 times the distance from the Earth to the Moon. 65 moon journeys, silently added or removed depending on which meaning of the word average happened to be in the sentence. The reason the true time average is larger is straightforward once you see it. Mars spends more of its life far from us than near us, because when the two planets are on opposite sides of the Sun, they linger there, and the geometry of two circles means most relative positions are not close ones. Something else is hiding in the ranges, and it is going to matter in a few minutes. Venus, at its nearest, comes closer to Earth than any other planet ever does, about 38 million kilometres. That is the smallest gap that exists between the Earth and anything except the Moon. Mercury, by contrast, never gets nearer than about 77 million kilometres, twice as far at best. Hold on to both of those figures, because in a moment they're going to be used to prove something that sounds impossible. The behaviour of the ranges changes as you move outward, and the change is instructive. For Mars, the swing is more than sevenfold, because Earth's own orbit is a large fraction of the total distance. For Jupiter, the separation runs from about 588 million kilometres to about 968 million, a factor of less than 2. For Saturn, roughly 1.2 to 1.67 billion. For Neptune, the separation only varies between about 4.3 and 4.7 billion kilometres, because Earth's entire orbit, the whole 300 million kilometre width of the year, is a plus or minus 1 part in 30 correction on a baseline of 30 astronomical units. That is a strange sort of consolation. The further away a planet is, the more honest its single number becomes, because your own motion stops mattering. Neptune genuinely does have something close to a fixed distance from us, in the sense that the variation is small compared to the total. Mars does not, and the planets that are near enough to be worth going to are exactly the ones whose distances are least stable. There is one more thing to say before we move on, and I'm going to say it now and then leave it alone for a while, because it does not belong here yet. Every number in this section is a distance. Kilometres, millions of kilometres, billions. But nobody experiences a distance. What people experience is time, and when you finally convert all of this into that unit, which we will at length, the answer stops being large and starts being something closer to a life sentence. It takes decades. I will leave that there for now. Because there is a more immediate problem. If the distance to a planet is not a number but a range, then the question, which planet is closest to us, has no obvious answer either. And when 3 engineers sat down in 2019 and worked out the answer properly, for the first time, the planet that came back was not the one that has been written in every textbook for 100 years. In March of 2019, 3 engineers published a short piece in Physics Today with a title that reads like a correction slip. It was called Venus is Not Earth's Closest Neighbour. Their names were Tom Stockman, Gabriel Munro, and Samuel Cordner. The piece was not long. It contained no new observations, no new instrument, no new data of any kind. Every number it used had been available for 200 years. What it contained was an argument that a calculation everybody had been doing was the wrong calculation, and that when you did the right one instead, the answer changed, not by a few percent, but to a different planet. Let me set up the mistake first, because it is beautifully ordinary. Ask how far Venus is from Earth on average, and here is what essentially every source does. Earth's orbit has a radius of 1 astronomical unit. Venus's has a radius of 0.723. Subtract one from the other, and you get 0.277 astronomical units, which is about 41 million kilometres. Do the same for Mars. 1.524 minus 1 is 0.524, about 78 million kilometres. Venus is closer. Therefore Venus is our nearest neighbour. Done, and repeated in textbooks, planetarium scripts, encyclopedias and documentaries for well over a century. Now look at what that arithmetic actually computed. It took the radius of one circle and subtracted the radius of another circle. That is the distance between the two orbits at their nearest points. It is the gap you would measure if both planets happen to be lined up on the same side of the Sun on the same day, which is a configuration that occurs for a moment and then does not occur again for over a year and a half. The rest of the time, the planets are somewhere else. Venus spends part of its life on the far side of the Sun, at which point it is not 41 million kilometres away, but 261 million. And the geometry of two circles is such that most possible relative positions are not the close ones. The near alignment is one narrow slice of a very wide range of possibilities, and the traditional calculation had quietly assumed the whole planet lives in that slice. Stockman, Monroe, and Cordner replaced it with something they called the point circle method. The idea is to stop asking about a moment and ask about all moments at once. Treat each orbit as a circle. Treat them as sharing a plane and a centre, which is very nearly true for the planets, and then compute the average distance from a point on one circle to every position on the other, weighted properly by how much time is spent at each. The result is not a simple subtraction. It comes out as an expression involving what mathematicians call a complete elliptic integral of the second kind, which is a piece of machinery from the 18th century that exists precisely for problems about the geometry of ellipses. In plain terms, the average distance is a function of the sum of the two radii, adjusted by a factor that depends on how similar the radii are. You do not need the formula to follow what happens next. What happens next is that they checked it, which is the part I find most satisfying. They did not simply trust an elegant expression. They ran a brute force simulation using a piece of astronomy software called PyFM, computing the actual positions of the planets every 24 hours for 10,000 years, something on the order of 3.5 million position samples for each pair of planets, and then just measured the distances and averaged them. No cleverness, just counting. The point circle method agreed with the simulation to within 1%. The traditional subtract the radii method was off by as much as 300%. And the ordering of the planets came out differently. Here are the real numbers. The average distance from Earth to Mercury is 1.04 astronomical units. The average distance from Earth to Venus is 1.14. The average distance from Earth to Mars is about 1.69. Mercury is closer to us than Venus is. Not on its best day. Venus wins the best day easily, at 38 million kilometres against Mercury's 77. But over any span of time long enough to be called typical, Mercury is our nearest planetary neighbour, and it is not a close contest. The margin is around 15 million kilometres. The simulation makes it even more concrete. Over those 10,000 years, if you asked on any given day which planet is currently nearest to the Earth, the answer was Mercury about 47% of the time, Venus about 36%, and Mars about 17%. Mercury is not merely closer on average, it is the most frequent answer to the question by a wide margin, on roughly 1 day in 2. The reason, once stated, is so simple that it is slightly humiliating not to have seen it. Mercury is on a small orbit. It hugs the Sun. It never at any point in its year gets more than about 70 million kilometres away from the Sun. And Earth is also fairly close to the Sun, in the scheme of things, 1 astronomical unit. So the furthest Mercury can ever possibly be from us is Earth's distance plus Mercury's distance, which is not very much, about 208 million kilometres at absolute worst. Mercury is trapped in a small region near the Sun, and because we are also near the Sun, Mercury can never get far from us. Venus, on a wider orbit, swings much further out on its bad days. It wins the sprint and loses the marathon, and then the result generalises, in a way I find genuinely difficult to shake off. The paper states it explicitly. Mercury is the closest planet, on average, to each of the other 7 planets, not just to Earth, to Venus, to Mars, to Jupiter, Saturn, Uranus and Neptune. It is even the closest planet, on average, to Pluto. There is one world in this solar system that is on average nearer to everything than anything else is, and it is the smallest, hottest, most overlooked of the 8, pressed up against the star. Think about what that means for the mental image. In the diagram, Mercury is the little grey one on the left that nobody has anything to say about. In reality, it is the hub. If you were drawing a map of the solar system based on average nearness rather than on radial position, a map of who is close to whom, Mercury would be at the centre of it, connected to everything, and the Sun would be off to one side as a detail. That map has never been drawn either. I should be fair to the point circle method about its own limits, because being careful here is part of what makes the result trustworthy. It works as well as it does because the 8 planets happen to travel on orbits that are very nearly circular and very nearly in the same plane. Feed it something wildly eccentric or steeply inclined, and the approximation starts to fray, which is exactly why the authors did not stop at the elegant expression and went to the trouble of running 10,000 years of real positions to check. The method is not a replacement for computing the actual geometry. It is a shortcut that happens to be almost exactly right for the particular solar system we live in. And I want to be fair to the old calculation too, because there is something important buried in it. Subtracting the orbital radii is not a meaningless operation. It is simply the answer to a different question, and, as it turns out, a more useful one for anyone who actually wants to go somewhere. The difference between two orbital radii tells you something real about how much work is required to move from one orbit to the other, because that work depends on the sizes of the orbits, and not on where the planets happen to be standing on any particular day. So the number that got mislabeled as the distance to Venus for 150 years was, all along, quietly answering a question about energy. Nobody noticed, because nobody was asking about energy. Keep that thought somewhere accessible. In about half an hour it is going to come back and rearrange the entire map. I want to sit with the shape of this error rather than the fact of it, because the fact is a curiosity and the shape is something else. This was not a failure of data. Nobody was waiting for a better telescope. The information required to get the right answer was available to Kepler. Every quantity in that calculation was known to 3 decimal places before the invention of the light bulb. What happened was that a plausible-looking piece of arithmetic got written down, and it produced an answer that felt right, and then for something like 150 years nobody rederived it. It was copied. From textbook into textbook, from encyclopedia into documentary, from teacher into student into teacher, and every single time the answer was passed along it acquired a little more authority simply from having been said before. Until in 2019 3 engineers with no particular stake in the question did the sum properly and the answer was different. That is the part that should sit uncomfortably. Not that Venus is not our nearest neighbour. That the fact you are most confident about in this whole subject, the one you would have bet money on, the one that felt too basic to be wrong, is the one that turned out to be wrong. And it was wrong for the least dramatic reason available, because it was simple enough that everyone assumed someone else had checked. So we have lost the number in the last part, and now we have lost the ranking. The distance to a planet is not a value, and the planets cannot be ordered by nearness in the way anyone assumed. But at least, you might reasonably think, we know the direction. Whatever the distance is on a given day, the planet is over there, and if you wanted to go, you would point at it and leave. You would not. Nobody ever has, and that is the second of the 4. No spacecraft in the history of the human species has ever travelled to another planet. Not one. What they have done instead is something that sounds like a philosophical quibble, and turns out to be the single most important fact about interplanetary distance. They have changed orbits. Here is the situation you are actually in when you leave Earth. You're not sitting still on a platform with a planet hanging in the sky in front of you. You are already moving at 29.78 kilometres per second in a very large circle around the Sun. So is your destination, on a different circle, at a different speed. Neither of you is stationary and neither of you can stop. There is no direction you could point in, and no engine you could build that would let you travel in a straight line from one to the other, because the moment you leave, you are still in orbit around the Sun. You have simply changed which orbit. Everything about interplanetary travel follows from that, and the person who worked out what to do about it was not an astronomer. He was a German architect. Walter Hohmann published a book in 1925 called The Attainability of Celestial Bodies. He had been thinking about the problem for years, in the evenings, while working as a municipal building surveyor in Essen. And what he found is that if you want to move from one circular orbit to a larger one using as little energy as possible, there is a specific and elegant way to do it. You fire your engine once, briefly, in the direction you're already travelling. That does not aim you at anything. It simply makes your orbit around the Sun bigger, stretches your circle into an ellipse whose near point is where you are now, and whose far point touches the orbit you want to reach. Then you shut the engine off, and you coast, for months, or years, and when you arrive at the far end of that ellipse, you fire once more to settle into the new orbit. That is a Hohmann transfer, and it is still, a century later, essentially how everything gets anywhere. Notice what it does not involve. It does not involve pointing at the target. It does not involve steering. It does not involve holding a course. The overwhelming majority of an interplanetary journey is spent with the engines off, falling, on a path that was fully determined in the first few minutes. Which means the entire question of reaching another world reduces to a single problem in timing. You must arrange for the far end of your ellipse to touch the target's orbit at precisely the moment the target happens to be passing that point. You do not aim at the planet, you aim at where it will be. Let me put you inside it for a moment, because this is the thing that diagrams cannot convey. You're aboard a spacecraft bound for Mars. The engine has been burning for a few minutes and now it stops. The silence is total, and it is permanent. That was the whole burn, and there will not be another one that matters for 259 days. You look out. Mars is not in front of you. Mars is off to one side, well off, a small orange point nowhere near the direction you're travelling. You're not moving toward it, and you will not move toward it for months. What you're doing is falling around the Sun on a wider, slower loop than the Earth's, and Mars has an appointment 8.5 months from now at the far end of it. Nobody is flying this thing. Nobody will touch the controls. The distance between you and Mars is going to increase for a while before it decreases, and in the most important sense, you have already arrived. Every consequential decision about this journey was made before the engine shut down, and everything after it is patience. Now, the arithmetic of that ellipse, because this is where the second of the four becomes a number. A Mars transfer runs from 1 astronomical unit at the near end to 1.524 at the far end. You ride half of it. If you work out the length of that arc, the actual path through space, the distance travelled, it comes to something on the order of 590 to 600 million kilometres. Hold that against the gap. Mars at its closest is 54.6 million kilometres from Earth. So the journey is roughly 10 times longer than the distance. That is the second layer, and it does not go away with better engineering. It is geometry. You cannot take the short way, because there is no short way. There is only the shape of the orbits you're moving between, and the minimum energy transfer times, once you accept the shape, are brutal in a very orderly way. To Venus, 146 days. To Mars, 259 days. To Jupiter, 2.73 years. To Saturn, 6.05 years. To Uranus, about 16 years. To Neptune, about 30.6 years. That last one deserves a moment. A minimum energy trip to Neptune on a Hohmann transfer takes 30 years. A person could begin such a mission at 25 and be 55 when the spacecraft arrived, having done nothing in between but wait. Real missions do not fly pure Hohmann transfers because 30 years is unacceptable and because there is a trick available. But the trick makes the path longer, not shorter, and this is where the numbers stop sounding theoretical. Cassini went to Saturn. Saturn's orbit sits 1.43 billion kilometres from the Sun. The distance Cassini actually travelled to get there was 3.5 billion kilometres, nearly 2.5 times the target's own distance from the star it orbits, and the route it took to accumulate that distance is almost comic. To reach Saturn, Cassini first flew inward, toward Venus, twice. It passed Venus in April of 1998, came back and passed Venus again in June of 1999, then swung past the Earth in August of that year, then out to Jupiter in December of 2000, and only then had enough speed to coast to Saturn. A spacecraft whose destination was 1.5 billion kilometres out spent its first 2 years going the wrong way. Juno went to Jupiter. Jupiter's orbit sits 778 million kilometres from the Sun. Juno travelled 2.8 billion kilometres, a path 3.5 times longer than the distance from the Sun to its destination. And Messenger went to Mercury. The planet that we established 20 minutes ago is on average our nearest neighbour in the entire solar system. Messenger covered something on the order of 8 billion kilometres to get there. It made 6 planetary flybys, 1 past Earth, 2 past Venus, 3 past Mercury itself, and looped around the Sun roughly 15 times over 6.5 years. 8 billion kilometres to reach a world that comes within 77 million kilometres of us. That is a ratio of about 100 to 1. To visit the house next door, it drove the equivalent of 100 round trips to the far end of the street. I want to name the reason this happens, because it is not incompetence, and it is not caution. Those spacecraft took long routes for the same reason a heavy lorry takes a long run at a hill. They were buying speed they could not afford to carry, and the only place to buy it is from a planet's gravity, and planets are not conveniently arranged, which we will come to properly in a moment. But there is a second reason the paths are long, and this one is written into the laws of motion rather than into any engineering constraint. It comes from Kepler, and it is the quiet sting in this whole section. Kepler's third law relates how long a planet takes to go around the Sun to how far out it is. The further out you go, the slower everything moves. Mercury travels at 47.36 kilometres per second. Venus, 35.02. Earth, 29.78. Mars, 24.07. Jupiter, 13.06. Saturn, 9.68. Uranus, 6.80. Neptune, 5.43. Read that list twice because it means distance charges you twice for the same journey. The path to a far planet is longer, which is obvious, but the far planet is also moving more slowly, which means the orbit you have to enter to match it is a slow orbit, which means the whole outer solar system operates on a lazier clock than the inner one. Neptune drifts along at 5.5 kilometres per second. That is slower than the launch speed of a large amateur rocket. The outermost planet in the solar system moves more slowly than the machines we throw at it, and it still takes decades to catch, because the distance is doing all the work and the speed is doing none of it. And there is a cruel symmetry hidden in that speed list. When you climb outward on a transfer ellipse, you arrive at the far end moving slowly. That is what climbing does, it trades speed for height. But the planet you're trying to meet is also moving slowly, in a different direction, and the two slow motions do not automatically agree. So at the end of a journey of billions of kilometres, having coasted for years, you arrive needing to change your velocity again, in order to stop being a thing that is falling past Saturn and become a thing that is going around it. That second burn is not a formality. It is often the most expensive part of the entire mission, and it is why the majority of the outer planets have only ever been photographed in passing rather than orbited. I should say something about Walter Hohmann himself, because his story belongs in a video about how long these journeys take. He worked this out in his spare time in the 1920s, as a hobby, in a country and a decade with no space program of any kind and no prospect of one. He published it, and it was read by a small circle of enthusiasts, and then it sat. Hohmann died in March of 1945, 12 years before anything humans built reached orbit at all. Every spacecraft that has ever gone to another planet has used his method. He never saw a single one of them leave the ground, and the transfer orbit that carries his name was a piece of pure geometry for the whole of his life. There is one more consequence I want to draw out, and it is the one that makes the second layer feel less like arithmetic, and more like a constraint on what kind of thing space travel can be. Because the whole journey is a single unpowered fall, arranged in advance, the vehicle is committed. There is no significant course correction available, no changing your mind, no diverting to somewhere nearer if something goes wrong. Trajectory correction maneuvers exist and they are real, but they are measured in meters per second against a journey measured in tens of kilometers per second. They refine the aim, they do not change the destination. Once the burn is over, the spacecraft is a thrown stone with a computer on it. Everything the mission will ever be was decided in the first few minutes, years before it arrives, and that is only possible if you are allowed to throw it at the right moment. Which brings us to the part of this that most people have never thought about at all, and which turns the distance into something worse than a distance, a schedule. Because you cannot begin this fall whenever you feel like it. The door is not always open. There is a sentence that gets said in mission control rooms and almost nowhere else, and it is one of the strangest sentences in engineering. It goes, "We missed the window, so we will try again in 2 years. Not next week, not next month, 2 years." This follows directly from everything in the last part. If reaching a planet requires arranging for the far end of your transfer ellipse to touch that planet's orbit at the exact moment the planet is passing, then the two planets have to be in a specific relative arrangement when you leave. Not when you arrive, when you leave, because after the burn nothing can be changed, and because both planets are going around the Sun at different rates, that arrangement comes and goes on a fixed cycle. For Mars the cycle is 779.9 days, 2.14 years, about 26 months. That number governs everything humans have ever done at Mars and everything we will ever do there. Every rover, every orbiter, every lander, every sample return concept, every crude mission architecture anyone has ever drawn, all of them are scheduled around a door that opens once every 26 months, and the door does not stay open long. The practical launch window, the span of days on which a viable trajectory exists with the propellant you have actually got, is typically 2 to 4 weeks. So the situation is this: a 2 to 4 week opportunity, recurring on a 26-month cycle, and if the rocket has a fault, or the weather is wrong, or a software review turns up something unresolved, the cost is not a delay of days. It is a delay of 2 years and 2 months, during which several hundred people continue to be employed on a spacecraft that is sitting in a clean room. That has happened. Repeatedly. It is one of the routine facts of planetary exploration that almost never makes it into the public account, because the public account is about the arrival. If you want to see the 26-month cycle written across the surface of world events, look at July of 2020. In that single month, 3 separate missions from 3 separate nations left for Mars. The United Arab Emirates launched the Hope orbiter on the 19th. China launched Tianwen-1 on the 23rd. The United States launched Perseverance on the 30th. 3 space programs, on 3 continents, with entirely different budgets, politics and objectives, all departing inside 11 days of each other, not through coordination and not through competition, but because the door was open and would not open again until late 2022. The calendar of Martian exploration is not set by anyone's ambitions. It is set by orbital geometry, and everyone simply queues for the same fortnight, and there was a 4th mission that should have been in that convoy. The European and Russian ExoMars rover was scheduled for the 2020 window, ran out of time on parachute testing and software validation, and stood down to the next opportunity in 2022. It did not fly in 2022 either, because by then the partnership had collapsed. The rover, fully built, has been waiting in a clean room for years. A schedule slip that in almost any other field of engineering would have been an inconvenience of a few months became, because of the 26-month cycle, a slip long enough for the geopolitical ground underneath the mission to shift and swallow it. That is what the window costs when you miss it. Not 2 years of waiting. 2 years of everything else being allowed to happen. The outer planets behave completely differently, and the reason is quietly delightful. A launch window recurs at the synodic period, the time it takes for the 2 planets to return to the same relative arrangement. For Mars, that is 780 days, because Mars is close enough to us that it takes Earth a long time to lap it. But Jupiter's synodic period is 399 days, Saturn's is 378, Neptune's is about 367 days, barely more than a year. The further out a planet is, the less it moves while we're going around, so we lap it almost exactly once a year, and the geometry comes back around almost annually, which produces an odd inversion. Windows to Mars are rare. Windows to Neptune are nearly always available. The constraint on the outer solar system is not when you can leave, it is how long you will be gone, and that number is measured in decades. Now the other piece of apparatus, and this is the one that turns the second layer from a problem into a strategy. If you cannot afford the speed you need, and you almost never can because propellant is charged at a punishing exchange rate we will get to shortly, you can steal it, not from nothing, from a planet. The idea is due to a graduate student. In 1961, a young mathematician named Michael Minovich was working at the Jet Propulsion Laboratory during a summer placement, with access to what was then one of the fastest computers in the world. He was interested in the restricted 3-body problem, which had a reputation for being analytically hopeless. What he worked out by brute numerical exploration was that a spacecraft passing close to a moving planet does not simply get deflected. It can leave with more speed relative to the Sun than it arrived with, because the planet's own orbital motion drags it along, and the tiny amount of momentum the planet loses in exchange is utterly negligible against its enormous mass. Nothing is created. The spacecraft is borrowing from the planet's orbit around the Sun, and the planet slows by an amount too small to measure. A few years later, in 1964 and 65, another young researcher at JPL named Gary Flandreau took Minovich's technique and asked a specific question. Were the outer planets ever arranged so that a single spacecraft could visit several of them in sequence, each one flinging it onto the next? And the answer was yes, but only in a narrow span of years in the late 1970s. That alignment of Jupiter, Saturn, Uranus and Neptune recurs roughly every 176 years. Flandreau had found it about 12 years before it opened. The Voyager program exists because 2 men in their 20s noticed a door that would be shut again for the rest of human history, and would not reopen until the 22nd century. It is worth stating plainly what that means. If the human species had developed spaceflight 50 years earlier, or 50 years later, the Grand Tour would not have been available, and Uranus and Neptune would very likely still be unvisited today. Voyager 2 flew through a gap in the timetable that happened by coincidence to coincide with the 2 decades in which we first became capable of using it. The first spacecraft to actually use the technique to reach another planet was Mariner 10 in 1974. It swung past Venus in order to reach Mercury, becoming both the first gravity assist mission and the first spacecraft to visit 2 planets. The maneuver worked, and within a decade it had gone from a novelty to a requirement, because once you know it is possible, no funding agency will pay for the propellant to do it the direct way. There is a related trick worth naming because it explains something about the shape of these routes. It is called the Oberth effect, after Hermann Oberth, and it says that a given amount of propellant buys you more energy if you burn it while you're already moving fast. Speed, in orbital mechanics, compounds. Which is why so many of these trajectories dive inward before climbing outward. The fastest place in the solar system to fire your engine is far down inside a gravity well, moving quickly, and that is why Cassini's route to Saturn went past Venus twice. Let me put the full absurdity of Cassini's itinerary in one place, because it is the best illustration of what launch windows and gravity assist do to a journey. Launch, the 15th of October 1997. Venus flyby, the 25th of April 1998. Venus again, the 24th of June 1999. Earth, the 17th of August 1999. 2 years after launch, back where it started, only faster. Jupiter, the 30th of December 2000. And Saturn orbit insertion on the 1st of July 2004 at 12 minutes past 9 in the evening universal time. 6 years and 8.5 months, 4 planetary encounters, 3.5 billion kilometers, and the first 2 years of it spent flying in the opposite direction to the destination. But the mission that shows most clearly what this costs is happening right now, and it is going to the nearest planet. Bepi Colombo launched on the 20th of October 2018 headed for Mercury. Because of the gravity well problem, which is the third layer and which we are about to meet properly, Mercury cannot simply be flown to. You have to shed velocity, enormous amounts of it, and the only affordable way to shed it is to keep flying past planets in the braking direction. So Bepi Colombo's itinerary includes 9 planetary flybys, 1 past Earth in April of 2020, 2 past Venus in 2020 and 2021, and 6 separate passes of Mercury itself between 2021 and 2025, 6 times arriving at the destination and deliberately not stopping. It was supposed to arrive in December of 2025. In April of 2024, the thrusters on its transfer module began underperforming. The cause was traced to unexpected electrical currents running between the solar array and the power distribution unit. The flight dynamics teams replanned the route, using closer Mercury flybys to squeeze out additional gravitational braking, and the full science mission was preserved. But the arrival slipped by 11 months. Mercury orbit insertion is now scheduled for the 21st of November, 2026. Total transit time, 8 years and 1 month. 8 years, 9 flybys, and a fault in a power distribution unit costing 11 months, to reach the planet that is on average the closest thing to us in the solar system. So the second layer is not just that the path is longer than the gap, it is that the path has a timetable, and the timetable is not negotiable, and the price of missing it is measured in years of human working life. The solar system is not open, it has scheduled openings, and you queue. But none of this yet explains why Mercury should be so hard. It is right there, it is the closest planet 47% of the time, and reaching it costs more than reaching Saturn. That is the third of the 4, and it is the one that rearranges the map. Let us step back for a moment and put the pieces on the table together, because we are about halfway through, and the shape of this is starting to matter more than any single fact in it. We began with a number under a picture, and found that it described an orbit rather than a distance. Then we found that the picture itself was compressed by a factor of thousands, and that an honest one requires a dry lake bed. Then we removed the number entirely, because the gap between 2 planets is a function of the date and swings by a factor of 7 for Mars. Then we lost the ranking, because when you average correctly, the nearest planet to Earth is Mercury, and Mercury is also the nearest planet to everything else. And then we lost the straight line, because no spacecraft has ever crossed a gap. They change orbits, along arcs 10 times longer than the distance, on a timetable that opens for a fortnight every 26 months. All of that is still, in a sense, about space, kilometres, and geometry, and calendars. Now we throw away the kilometres, because they were never the real currency. Here is the thing that took me a while to properly absorb. If you asked a mission designer at any space agency in the world how far away Mars is, they would not answer in kilometres. They would answer in kilometres per second, not distance, change in velocity. The technical term is delta V, and it is the total amount of velocity change a spacecraft must be able to produce over the course of a mission. That single quantity determines whether a mission is possible, how large the rocket must be, how much it costs, and in most cases whether it happens at all. The reason delta V rules everything is the rocket equation, and the rocket equation is unkind in a very particular way. Because a rocket must carry its own propellant, and that propellant has mass, and accelerating that mass requires more propellant, the relationship between the velocity you want and the propellant you need is not linear. It is exponential. Every additional kilometre per second of capability costs you a multiplicative increase in the mass you have to launch, which means that in space travel, small differences in required velocity turn into enormous differences in what is buildable, and the same amount of propellant that gets you comfortably to one destination may not get you to another that is closer. So let us look at the actual figures, and I want to flag up front that these are approximate. Published values vary depending on assumptions about parking orbits and capture altitudes, and the ones I am using are computed from standard gravitational parameters rather than quoted from a single source. Treat them as the right size, not to 3 decimal places. Starting from a low Earth orbit 200 kilometers up, the velocity change required to depart for a Mars transfer is about 3.61 kilometers per second. To depart for Jupiter, about 6.31. To depart for Saturn, about 7.29. Those scale roughly the way intuition would expect. Further out, more expensive. But departing is only half the job, and it is the cheap half. If you actually want to stay, to enter orbit around the destination rather than fly past it and keep going, you have to stop, and roughly half the velocity budget of an orbital mission is spent on stopping rather than on going. This is the single most underappreciated fact in interplanetary travel. Getting there is not the problem. Arriving is the problem. Now watch what happens when we do the full accounting. Mars, about 3.61 kilometers per second to leave, plus about 2.10 to capture into orbit. Total, roughly 5.7 kilometers per second. Mercury, about 5.55 kilometers per second to leave, already more than Mars, and then, to capture, about 7.55 more. Because when you arrive at Mercury, you're moving with an excess velocity of something like 9.61 kilometers per second relative to the planet, and every bit of that has to be thrown away. Total, roughly 13.1 kilometers per second. Mercury, the nearest planet to Earth on average, the planet that is nearest to every other planet in the solar system, costs about 2 1/3 times as much velocity to orbit as Mars, a world nearly 4 times further out, and it is comparable to, or worse than, the cost of injecting towards Saturn, Uranus, or Neptune. Let me convert that difference into something physical, because kilometers per second is an abstraction until you see what it does to a vehicle. Take a good chemical rocket stage with an effective exhaust velocity of about 4.4 kilometers per second. That is roughly what the best practical propellant combinations deliver. To achieve Mars's 5.7 kilometers per second, the rocket equation says your vehicle has to be about 3.5 times heavier at the start than at the end, which means around 3/4 of everything you launch is propellant. That is demanding but entirely normal. Every rocket ever flown looks something like that. Now to Mercury's 13.1, the mass ratio jumps to roughly 20. About 95% of the vehicle has to be propellant. You have gone from a spacecraft that carries a lot of fuel to a fuel tank that carries a rumour of a spacecraft. That factor of 2 1/3 in velocity became a factor of 5.5 in mass, and it is why nobody flies to Mercury directly. Both Messenger and Bepi Colombo chose instead to pay in time, 6.5 years and 6 flybys for the first, 8 years and 9 flybys for the second, because time is the one currency in interplanetary travel that can be substituted for propellant. That trade is the whole reason this video has the answer it has, and there is one more asymmetry that explains why Mars is cheap in a way that has nothing to do with distance. Mars has an atmosphere, a thin one, only about 1% of Earth's at the surface, but it is enough to break against, and every successful Mars mission has used it, converting velocity into heat in a shield rather than buying that velocity change with propellant. Mercury has no atmosphere at all. Neither does the Moon. On worlds with no air, every last meter per second of arrival speed has to be cancelled by an engine, carrying propellant you launched from Earth years earlier. The presence or absence of a thin layer of gas is worth more, in the accounting that actually matters, than 200 million kilometers of position. The reason is gravity, and specifically the shape of the Sun's gravity well. We tend to picture the solar system as a flat map with the Sun as a landmark. It is not flat. It is a funnel. The Sun sits at the bottom of an enormous gravitational depression, and every planet sits on the slope of it, and the closer to the Sun you are, the deeper down you are and the faster you must move to avoid falling in. That is why Mercury travels at 47 kilometers per second and Neptune at 5. Going outward means climbing, which costs energy but hands you a gentler arrival, because you are slowing down as you climb. Going inward means falling, which gives you speed for free, and then presents you with a bill, because all of that free speed has to be destroyed before you can stop. Falling is easy, landing is not. So the map that mission designers actually use does not look like the diagram at all. On the diagram, Mercury is the nearest thing and Neptune is the furthest. On the Delta V map, Mercury and Neptune sit at comparable difficulty. The Moon is far cheaper than either, despite being the only place we have physically stood, and Mars, significantly further away than Mercury by every distance measure we have discussed, is one of the most accessible destinations in the entire solar system, which is a large part of why our robots keep going there. The diagram is not the distance. It never was. And this is the version of that sentence I actually wanted to arrive at, because it is stronger than the one in the first part. Earlier I said the picture had the wrong numbers on it. Now I can say something more precise. No drawing of the solar system can encode how hard it is to get anywhere, because difficulty is not a spatial property. It is a property of velocity, and velocity does not appear on maps. You could draw the positions of all 8 planets to perfect scale on a lake bed, and the drawing would still tell you nothing about which of them you could reach. And do you remember the mistake from part 4? The one that had Venus as our closest neighbour for 150 years, obtained by subtracting one orbital radius from another? That calculation was not the answer to the question everyone thought they were asking. But it was, silently, the answer to this question. The difference between 2 orbital radii is a decent first indication of how much orbital energy you have to change, because energy depends on the size of the orbit, and not on where the planet is standing today. For a century and a half, textbooks were printing an energy figure and labelling it a distance, and it went unnoticed because nobody was thinking about energy. The wrong answer to one question was quietly the right answer to a better one. 2 more numbers to anchor how expensive velocity really is. To escape Earth's gravity entirely from the surface requires about 11.186 kilometers per second. To escape the Sun's gravity from where the Earth is requires about 16.6. Those are the walls of the room. Everything humans have ever launched has had to pay something in that range simply to be allowed to leave, before a single kilometre of the actual journey is credited. Which brings us to the obvious question, and it is the one I suspect has been forming for a while. If distance is not the constraint and geometry is not the constraint, and the real constraint is how much velocity you can buy, then how much can we buy? What is the fastest we have ever managed, and what does it get us? The answer to the first part is genuinely impressive. The answer to the second part is the sound of a door closing. On the 19th of January 2006, an Atlas V rocket lifted off from Cape Canaveral carrying a spacecraft about the size and shape of a grand piano, and it went faster than anything humans have ever thrown. New Horizons left the Earth at 16.26 kilometers per second, 58,536 kilometers per hour. It remains, 20 years later, the highest launch speed ever achieved by a spacecraft, the record for how fast a thing has ever been made to leave this planet. To put that in a frame the body can hold, at that speed you would cross the Atlantic in about 6 minutes, and the distance from the Earth to the Moon in roughly 6.5 hours. Apollo took 3 days, and it was not enough. Because even at the fastest departure velocity in the history of rocketry, aimed directly outward with a target chosen partly because it required so little manoeuvring, New Horizons could not reach Pluto in a reasonable time on its own. It needed help. 13 months after launch, on the 28th of February 2007, it swung past Jupiter and stole roughly 14,000 kilometers per hour from the largest planet in the solar system. That assist cut about 3 years off the journey, so the fastest launch ever achieved, plus a gravitational theft from Jupiter, plus a route designed for speed rather than for science, still added up to a trip that took 9.5 years. We will do that arithmetic properly in a moment. For now, hold the shape of it. Our very best effort, fully optimized, and the answer was most of a decade. Now, the outright speed record, because it is a wonderful number, and it does something instructive. The fastest speed ever reached by any object built by human beings is 192.22 kilometers per second, 692,000 kilometers per hour, 430,000 miles an hour. It was achieved by the Parker Solar Probe at 11:53 and 48 seconds, universal time on the 24th of December, 2024, as it passed 6,167,590 kilometers above the surface of the Sun. It is a certified world record, and it still stands. 192 kilometers per second is a genuinely extraordinary speed. At that velocity, you could cross the continental United States in about 25 seconds. You could go from the Earth to the Moon in half an hour, and it is completely useless for going anywhere. Here is why, and it is the gravity well again. Parker is not fast because of its engine. Parker is fast because it fell. It is at the bottom of the Sun's gravitational funnel, having traded height for velocity, and that speed is not an asset it owns. It is a loan. Every kilometre per second of it will be handed straight back as the probe climbs away from perihelion. Parker cannot take that speed and go to Neptune, any more than a cyclist at the bottom of a hill can take their speed and go up a mountain. The velocity exists only at that location, and it exists precisely because that location is the worst possible place to start a journey outward from. Compare Voyager 1, which is travelling at about 17 kilometres per second, 11 times slower than Parker's record. But Voyager owns it. That 17 kilometers per second is above solar escape velocity. It is not borrowed and it will not be repaid. Voyager will still be doing roughly that in 100,000 years, which is why the slowest sounding number in this section is the only one that has ever actually taken anything out of the solar system. So that is the ceiling. 16.26 kilometers per second on the way out, if you spend everything you have on speed and nothing on payload. 17 if you accept a gravity assist and a 50-year mission. Somewhere in that region is the honest answer to how fast humans can currently make things go outward, and it is not going to change dramatically in your lifetime. I should be honest about what could improve, because it will not change in your lifetime is a strong claim, and it deserves the evidence. There are 4 candidate technologies, and none of them break the problem open. Nuclear thermal propulsion heats hydrogen through a fission reactor instead of burning it, which roughly doubles the effective exhaust velocity, a specific impulse of around 900 seconds against a chemical rocket's 450. That would take a Mars transfer from something like 7 to 9 months down to perhaps 4, and would widen the launch window, because a faster crossing is less dependent on perfect alignment. Engines of this type were built and ground-tested in the 1960s and 70s, around 20 of them, and every one of the programs was cancelled before flight. Half a century later, there is finally a serious attempt to fly one. A factor of 2 is a genuine improvement. It is not a factor of 10. Electric propulsion inverts the trade. Ion engines and Hall-effect thrusters achieve exhaust velocities several times higher than any chemical rocket, but produce thrust measured in fractions of a newton, about the weight of a sheet of paper on your hand, applied continuously for years. Dawn used ion propulsion to become the only spacecraft ever to orbit 2 separate worlds beyond Earth, Vesta and then Ceres, and it could only do that because the efficiency removed the impossible mass ratios. Electric propulsion does not make journeys dramatically shorter. It makes destinations possible that were previously unaffordable, which is a different kind of gain. Aerocapture attacks the expensive half of the problem, the stopping, by doing all of it in a single pass through a planet's atmosphere instead of with an engine. It has never been attempted. It sits in outer planet mission studies year after year precisely because it would cut years from a Uranus or Neptune trajectory, and it stays unflown because the margins are unforgiving. Too shallow, and the spacecraft skips off and escapes. Too steep, and it burns. Solar sails carry no propellant at all, which is elegant, and their thrust falls off with the square of the distance from the Sun, which is fatal for the outer system. Sunlight at Neptune is roughly 1/900th of its intensity here. Sails are an inner system tool, and to mark the ceiling honestly, if you had a drive that could accelerate continuously at 1 Earth gravity, flipping over halfway to decelerate, you would reach Mars in about 2 days, and Neptune in about 2 weeks. That is the solar system everyone imagines. It requires a velocity budget in the thousands of kilometers per second, which is not a hard engineering problem but a different category of thing entirely, several orders of magnitude beyond any concept with a physical basis. The gap between the solar system we have and the solar system in our heads is not a factor of 2, it is a factor of hundreds, and it is sitting behind physics rather than behind ambition. Let me convert it into units the body actually understands, because this is where the four layers start to fuse. One astronomical unit is 150 million kilometres. If you walked it, at a comfortable 4 to 5 kilometres an hour without stopping, it would take about 3,400 years. You would have needed to set out before the Bronze Age ended to arrive now. If you drove it, at 100 kilometres an hour continuously, it would take around 170 years. 5 generations of drivers, changing shifts. If you flew it in a commercial airliner at 900 kilometres an hour, you would need about 19 years for that one unit, and something like 570 years to reach Neptune's orbit. The fastest that human beings themselves have ever travelled is the crew of Apollo 10 at about 39,897 kilometres per hour, roughly 11.08 kilometres per second, reached on the return from the Moon in 1969. That record has stood for 57 years. At the speed of the fastest humans who have ever lived, Neptune's average distance would take about 13 years. And that comparison lets me set down the human baseline for this whole video, which is the Moon. Apollo 11 launched on the 16th of July 1969. It entered lunar orbit at 75 hours and 50 minutes of mission elapsed time, about 3 days and 4 hours after leaving the ground. The landing came at 102 hours and 45 minutes, roughly 4.3 days in. Those two figures get conflated constantly, so it is worth separating them. 3 days to arrive in orbit, a bit over 4 days to touch down, 384,000 kilometres in 3 days. That is the only destination in this entire video that a human being has ever reached inside a single week. It is also, and this is the part that reframes it, about 1/400th of the way to Mars at its very closest. If you scaled the Apollo journey up to Mars's best case and kept the same speed, you would be travelling for something like 3.5 years, which is roughly what a Mars mission would take, out and back, with the wait for the return window included. And it is why every crude Mars architecture ever drawn is a multi-year commitment rather than an expedition. So here is where we stand. We know how fast we can go, we know it will not meaningfully improve soon, and we know the distances, the paths, and the velocity costs, which means it is finally time to convert all of it into the only unit that any human being has ever actually experienced a journey in. Not kilometres, not kilometres per second, years. Back in part 3, I said something and then deliberately left it alone. I said that when you finally convert all of this into the unit people actually experience, the answer stops being large and becomes something closer to a life sentence. It takes decades. I want to make good on that now, because we have everything we need. And I want to do it by simply reading out the record mission by mission, because the list makes the argument better than any framing I could put around it. New Horizons, launched the 19th of January 2006, at the highest departure speed ever achieved. Gravity assist at Jupiter 13 months later. Closest approach to Pluto on the 14th of July 2015, passing 12,500 kilometres above the surface. Elapsed time, 9 years, 5 months, and 25 days. Distance travelled, about 4.8 billion kilometres, 9.5 years, for the fastest thing we have ever launched on the most direct trajectory available with help from Jupiter. And I want to stay with New Horizons for a moment, because what happened at the end of those 9.5 years is the best illustration of this whole subject that I know. The spacecraft had one chance, a single flyby at 14 kilometres per second, with no possibility of slowing down or going back. And here is the constraint that makes it painful. New Horizons has one antenna and one set of instruments, and they cannot both point in useful directions at once. To photograph Pluto, the spacecraft had to point its instruments at Pluto, which meant pointing its antenna away from Earth. So during the encounter, the most important few hours of a mission that had consumed 9.5 years and roughly $700 million, the spacecraft could not communicate at all. It went silent on purpose. Picture the room. It is the 14th of July 2015 at the Applied Physics Laboratory in Maryland. There are several hundred people present. Some of them have worked on this for the whole 9.5 years, and a few have worked on it for longer than that, since the mission was a proposal that kept getting cancelled. The closest approach happens at 11:30 in the morning Eastern Time, except it does not happen then for them. The signal delay from Pluto is 4 hours and 25 minutes, so at the moment the encounter is theoretically occurring, it has in fact already occurred, 4.5 hours ago, and the light carrying the news is still in transit somewhere past the orbit of Neptune. Nobody in that room knows whether the spacecraft is intact. Nobody will know for a long time. They wait roughly 21.5 hours, not because of the signal delay alone, but because the spacecraft has been scheduled to keep observing, and only then to turn, find Earth, and report. So for most of a day, several hundred people sit with the knowledge that the answer already exists and cannot be reached. The flyby has either worked or it has not. It happened yesterday. It is finished, and it will keep being finished unknowably for another 20 hours. The signal locked at approximately 9 in the evening on the 15th of July. The room came apart, and then the data began to arrive at a few hundred bits per second across 4.5 light hours, and it took roughly 15 months to download it all. The encounter lasted hours. The downloading of the encounter took over a year. That is not a bandwidth problem. That is the distance, expressed in a fourth way we have not even reached yet. And the 9.5 years of flight is not even the whole span. It is the short part. Because a mission to Pluto had been fought for, unsuccessfully, for a very long time before anything left the ground. A group of scientists who called themselves the Pluto Underground began pressing for it at the end of the 1980s. Concept after concept was drawn up, costed, and killed. One design was abandoned as too expensive. Its successor was cancelled outright in the year 2000. New Horizons itself was only selected in November of 2001, and it survived the following years under repeated threat of cancellation. So by the time the signal locked in that room in Maryland, the elapsed time from the first serious attempt to go to Pluto was closer to 26 years than to 9.5. And the data kept arriving for another 15 months after that. There is one more detail about that mission which I find almost unbearably neat, and which says everything about what a decade of travel does to a project. New Horizons launched in January of 2006 to visit the 9th planet of the solar system. 7 months later, in August of that year, the International Astronomical Union voted on a formal definition of the word planet, and Pluto did not meet it. The spacecraft was already in flight, past the orbit of Mars, unreachable and uninstructable. It had left for one kind of destination, and it arrived 9 years later at a different kind. The target had not moved and had not changed in any physical respect. The category had changed underneath it, while the spacecraft was in transit, and nobody could tell it. That is a version of the distance problem that has nothing to do with kilometres. When a journey takes long enough, the world you left and the world you return your data to are not the same world. The meaning of the destination can shift mid-flight. Voyager has its own version of this. When Voyager 2 launched in 1977, the mission it had been funded and approved for ended at Saturn. Uranus and Neptune were not the plan. They were a possibility that the engineers had quietly protected. The spacecraft was built more robustly than the approved mission required, and the trajectory was chosen so that if the machine survived Saturn, and if a future budget said yes, the door to the outer two planets would still be open. It survived. The budget said yes. And so the only close-up images of Uranus and Neptune that exist in human history exist, because a group of people in the mid-1970s built something tougher than they were asked to, for a journey they had no authorization to make, on the chance that somebody a decade later would let them. Now, the rest of the list. Cassini. Launched the 15th of October 1997. Saturn orbit insertion the 1st of July 2004 at 12 minutes past 9 in the evening Universal Time. 6.7 years to arrive. Then 13 more years in orbit, until it was deliberately flown into Saturn's atmosphere on the 15th of September 2017 to make certain it could never contaminate a moon. A 20-year mission, of which a full third was spent simply getting there. Juno. Launched the 5th of August 2011. Jupiter orbit insertion the 4th of July 2016. 4 years and 11 months, 2.8 billion kilometres. Messenger. Launched the 3rd of August 2004. Mercury orbit insertion the 18th of March 2011. 6.6 years, 6 planetary flybys, 15 loops around the Sun, roughly 8 billion kilometres, to reach the nearest planet. Bepi Colombo. Launched the 20th of October 2018. Arriving at Mercury the 21st of November of this year, 8 years and 1 month, and Voyager 2, which is the one that turns this from a list of numbers into something else, launched the 20th of August 1977, Jupiter in July of 1979, Saturn in August of 1981, Uranus on the 24th of January 1986, 8 years and 5 months out, and Neptune on the 25th of August 1989, passing 4,950 kilometres above the North Polar cloud tops, 12 years and 5 days from launch to the last planet. There is the answer. That is what the distance to each planet actually is, once you have accounted for the moving target, the curved path, the timetable, and the velocity price. Not 58 million kilometres, or 228 million, or 4.5 billion. 5 years to Jupiter, 7 to Saturn, 8 to Mercury, 9.5 to Pluto, 12 to Neptune. It takes decades. And now I want to spend a little time on what that sentence does to people, because the machines do not care and the people do. Consider Edward Stone. He was a physicist at Caltech, and in 1972 he was appointed project scientist for a mission that did not yet have spacecraft, to visit planets nobody had ever seen closely. He was 36 years old. When Voyager 2 launched in 1977, he was 41. When it reached Uranus in 1986, he was 48, standing in front of the world's press explaining images of a world that had been a smudge in a telescope for 2 centuries. When it reached Neptune in 1989, he was 53, and that was the last planet, and everyone knew there would never be another first look at another planet in their lifetimes. He stayed. He remained Voyager's project scientist for another 33 years. He handed the role to someone else in 2022 at the age of 86 after 50 years in the job. He died in June of 2024 at 88. Both spacecraft are still transmitting. That is what the distance costs. Not the propellant, not the money, a human being's entire working life, start to finish, spent on a single crossing that outlived him and is still going. And Edward Stone is not an unusual case. He is the clearest case. Every outer planet mission has people like this. Engineers who joined a Uranus orbiter study in their 30s, knowing that if it ever flies, the data will arrive after they retire. Instrument designers who will never see their instrument switched on. The standard planetary science career is shorter than the standard outer solar system journey, and everybody in the field knows it and does the work anyway. Back in part 5, I said that a spacecraft does not aim at the planet. It aims at where the planet will be. I want to hand that sentence back now in its other form. The people who build these things are doing exactly the same thing with their own lives. They are not aiming at where they are. They are aiming at a position their life will occupy in 15 or 20 or 30 years, and committing to it in advance, unpowered, with no course corrections available. Some of them arrive, some of them do not. So we have the answer in years. But the distance has one more layer, and it is the strangest of the 4, because it is the only one that no engine will ever shorten, and no clever trajectory will ever avoid. Before we get to it, though, there is something about the arrangement of these distances that makes the decades worse than the arithmetic suggests, because the solar system is not laid out to give you any sense of progress at all. The 8 planets are not evenly spaced, and the way in which they are not evenly spaced is worth going through slowly, because it produces a fact that I did not believe the first time I calculated it. Let me list the gaps, not the distances from the Sun, the gaps between neighbours, measured in astronomical units. From the Sun out to Mercury, 0.387. Mercury to Venus, 0.336. Venus to Earth, 0.277. Earth to Mars, 0.524. 4 steps, and we have travelled 1.5 astronomical units. Half the planets in the solar system are behind us. If the spacing continued in that manner, Neptune would be somewhere around 3 astronomical units out, and the whole system would be a tidy neighbourhood, roughly twice the size of Mars's orbit. Then the pattern breaks. Mars to Jupiter, 3.68 astronomical units. In a single step, 7 times the Earth to Mars gap. Everything we have discussed so far, the entire inner solar system, all 4 rocky planets, every world a human being has ever set foot on or sent a rover to, fits inside a distance less than half of this one gap, and the gap contains the asteroid belt, which sounds like it might fill it, and does not. The total mass of every object in the belt combined is only about 4% of the mass of our moon. It is the emptiest crowded place in the solar system, and every spacecraft that has ever flown through it has done so without any special precautions, because the odds of encountering anything at all are negligible. Jupiter to Saturn, 4.379, already larger than the whole inner solar system and the Mars to Jupiter gap put together. Saturn to Uranus, 9.618. Uranus to Neptune, 10.85. Now hold those last 2 against something. The distance from the Sun to Saturn, The whole of it, the Sun and Mercury and Venus and Earth and Mars and the asteroid belt and Jupiter and everything between them, the entire history of every world anyone has ever cared about, is 9.583 astronomical units. The gap between Saturn and Uranus is 9.618. Those two numbers are essentially the same. The gap slightly exceeds the distance by about 0.4%, so I want to be careful and say it correctly. The empty stretch between Saturn and Uranus is roughly equal to, and just a little greater than, the entire distance from the Sun out to Saturn. You could take everything from the star to the ringed planet, lift it out, and drop it into the gap between Saturn and Uranus, and it would fit with a little room to spare. And then the next gap is bigger. Uranus to Neptune is 10.85 astronomical units, which is unambiguously larger than the whole distance from the Sun to Saturn. Not marginally, comfortably. So here is the structure of the planetary solar system stated honestly. Somewhat more than 2/3 of its radius consists of exactly two empty stretches, each one about as wide as everything inside it, with a single planet standing between them. Uranus is not a landmark on a journey outward. Uranus is a solitary object in the middle of a very long nothing, with an equally long nothing on either side. Voyager 2 experienced this, and its own timeline is the proof, because the spacecraft did not slow down. It reached Jupiter in July of 1979. It reached Saturn in August of 1981, about 2 years later. It reached Uranus in January of 1986, 4.5 years after that, and it reached Neptune in August of 1989, 3.5 years after Uranus, having been given a substantial push by Uranus's gravity on the way through. 2 years, then 4.5, then 3.5. Same spacecraft, same velocity, no braking, no detours. The journey did not get slower. The solar system got wider underneath it. Let me put you in the long stretch, because it is the part of the Voyager story nobody tells. It is 1982. Voyager 2 left Saturn a few months ago, and Uranus is 4 years away. There is nothing to look at. The Sun behind you has shrunk to a very bright point, bright enough to hurt, small enough to cover with a pinhead, and the sunlight falling on the spacecraft is around 1% of what it was at Earth. Jupiter and Saturn are behind, receding, unremarkable points among the stars. Uranus is ahead, and it is also a point, and it will remain a point for years. It does not resolve into a disk that means anything until almost the end. The instruments are mostly off to save power. On Earth, the team has shrunk. People have moved to other projects. Presidents change. Children born in the year of the Saturn encounter start school and finish primary school before anything happens. The spacecraft is not waiting, because it does not experience waiting. It is simply falling at 17 kilometers per second through 4.5 years of nothing on its way to a planet that will occupy it for a few hours. There is something in that which the kilometer figures do not carry. The gaps are not merely long, they are structured so that you cannot feel yourself getting anywhere. Progress as a sensation requires landmarks passing at a rate your mind can register, and out there the landmarks are separated by intervals longer than the attention span of institutions. And there is a consequence of those two gaps that is still with us right now, and it is the most concrete thing in this entire video. Voyager 2 remains the only spacecraft that has ever visited Uranus or Neptune. Not the only one to orbit them, the only one to have been anywhere near them, ever, in the history of the species. Everything humanity knows about the two outermost planets from close range comes from a few hours of instrument time in January of 1986 and August of 1989, gathered by a machine designed with 1970s electronics, carrying a computer with less memory than a modern greetings card. The Uranus encounter has a footnote that has always stayed with me. Voyager 2 made its closest approach to Uranus on the 24th of January, 1986. 4 days later, on the 28th, the Space Shuttle Challenger broke apart shortly after launch. The first and only close look at the seventh planet, a genuinely unrepeatable event, the culmination of 8.5 years of flight, vanished from public attention almost immediately, and understandably so. It has never really come back. Most people have no idea it happened at all, and nothing has replaced it. There is no spacecraft en route to Uranus. There is no spacecraft en route to Neptune. There has not been one for 37 years. The planetary science community has repeatedly ranked a Uranus orbiter among its very highest priorities, on the straightforward grounds that we have a 40-year-old flyby of a world we do not understand, and the mission keeps being deferred. And the reason it keeps being deferred is exactly the subject of this video. A Uranus orbiter launched in the early 2030s would arrive in the 2040s. The transit time exceeds the planning horizon of the institutions that would have to pay for it. It is not that anyone thinks it is unimportant. It is that the gap between Saturn and Uranus is 9.6 astronomical units wide, and that translates into a commitment longer than any government, any budget cycle, and most careers. The gaps are not just empty. They are why the outer solar system has been visited once and then left alone for a generation. And I should say something about why the spacing is like this, because there is a reasonable expectation that it might be a law of nature, and it is not. There is an old observation called the Titius-Bode relation from the 18th century, which notes that the planetary distances follow a roughly geometric progression, each one about 1.5 to 2 times further out than the last. It describes the pattern reasonably well as far as Uranus, and then fails badly for Neptune, and it has never had an accepted physical explanation. It appears to be a coincidence that is almost, but not quite, a rule. The best current account of why the giant planets sit where they do is that they did not form there. The evidence points to a violent rearrangement in the early solar system, in which the outer planets migrated substantially from their birthplaces before settling into the configuration we see now, which means the 2 enormous gaps that define the limits of human exploration are not fundamental features of how planetary systems work. They are the frozen record of something that happened 4.5 billion years ago and then stopped. That is worth sitting with. Surveys of other stars have found compact systems with several planets orbiting closer in than Mercury, architectures where every world in the system would be reachable in months rather than decades. There is no law that says a solar system has to be arranged like a house, with 2 rooms at one end and 100 acres of field between them and everything else. Ours is. The specific arrangement that puts most of our own solar system permanently beyond a human working lifetime was set before there was anyone to be inconvenienced by it, and it could easily have been otherwise, so that is the geometry, in full. But we still have one layer left, and it is the only one with no engineering answer at all. Not a difficult answer. No answer. Because up to now, everything we have discussed could in principle be improved by building something better. The 4th distance cannot be. Everything we have discussed until now has been, in principle, negotiable. The paths could be shortened with better engines. The launch windows could be widened with more propellant. The velocity cost could be reduced by a factor of 2 with nuclear thermal propulsion, or bypassed with aerocapture. None of it is easy, but all of it is engineering, and engineering is the thing our species is actually good at. The 4th distance is not engineering. There is no version of the future in which it improves, because it is not a limitation of our machines. It is a property of the universe. Light travels at 299,792.458 kilometers per second, and nothing carrying information travels faster, which means that every distance in this video is also a delay, and the delay is not a technical inconvenience. It is a permanent feature of the geometry. Here is the ladder, one way, from Earth. To the Moon, 1.28 seconds. That is small enough to be almost conversational. Apollo transmissions have a noticeable pause in them, and if you listen to the recordings, you can hear people talking over each other and correcting for it. But it works. It is the last destination in the solar system where speech is possible. To the Sun, 8 minutes and 19 seconds, which means the sunlight on your skin left its source before you got up to look at it. To Mars, 3 minutes at closest approach, 22.3 minutes at its furthest, a round trip of between 6 and 45 minutes. To Jupiter, 32.7 minutes at best, 53.8 at worst. To Saturn, between about 1 hour and 7 minutes and 1 hour and 33 minutes, averaging around an hour and 20. To Uranus, between roughly 2 hours 23 and 2 hours 55. To Neptune, between about 3 hours 59 and 4 hours 20, which means a round trip to Neptune, a question asked and an answer received, takes over 8 hours. You could send a command to a spacecraft at Neptune, go to sleep, and the confirmation that it had been received would not yet have arrived when you woke up. And to Pluto, depending on where it is on its eccentric orbit, between about 4 hours and nearly 7. Now let me show you what those numbers do to a real operation, because the abstraction becomes something else when you watch it happen to people. On the 6th of August 2012, the rover Curiosity arrived at Mars. The arrival sequence was, and remains, one of the most audacious things ever attempted by an engineering team. Entry into the atmosphere at about 21,000 kilometers per hour, a heat shield, a supersonic parachute, then the discarding of the parachute, then a rocket-powered descent stage, and finally a maneuver in which the descent stage hovered and lowered a 1-ton rover to the surface on 3 cables before flying away to crash at a safe distance. It was designed to take about 7 minutes. The team called it the 7 minutes of terror. The one-way light time from Mars to Earth that day was 13 minutes and 48 seconds. Read those 2 figures together, and you will see the strangest control room situation in the history of exploration. The entire landing, every stage of it, the heat shield, the parachute, the sky crane, the touchdown or the crater, took 7 minutes. The news of it took nearly 14 to arrive, which means that at the instant the first signal reached Earth saying that Curiosity had begun entering the atmosphere, the landing had already been over for nearly 7 minutes. It had already succeeded or already failed. The outcome was fixed, unalterable and unknown. Picture that room. Several hundred people watching a screen that is showing them a past they cannot influence. Every person present understands that whatever they are about to learn happened a quarter of an hour ago, that the rover is at this moment either driving ready on the surface of Mars or a field of wreckage, and that there is not one action available to any of them that could affect which. They are not monitoring a landing, they are receiving a report about a landing, and so they sit and watch telemetry describe, step by step, an event that finished before the description started, and they applaud each stage as it is announced, knowing the applause is for something already historical. This is not an unusual case. Perseverance landed on the 18th of February 2021, with a one-way delay of 11 minutes and 22 seconds. The same arrangement again. And when the Huygens probe descended through the atmosphere of Titan on the 14th of January 2005, its descent lasted 2 hours and 27 minutes, and the signal delay was about 1 hour and 7 minutes. So the probe had been sitting on Titan's surface for well over an hour before the first data from the top of its descent reached anybody. This is also why every rover that has ever operated on another world has had to be substantially autonomous. Nobody drives them. It is a physical impossibility. A driver on Earth pressing forward and waiting to see what happens would be issuing commands to a machine whose situation is a quarter of an hour out of date, receiving pictures of a rock the rover has already either avoided or driven into. Teleoperation, the ordinary sense of remote control where you act and see the result, stops working past the moon and never starts working again. Voyager 1 is the limit case, and it is where this whole video has quietly been heading. It is currently about 170 astronomical units from Earth, on the order of 25.7 billion kilometers. The one-way signal time is roughly 23 hours and 50 minutes. The round trip is nearly 48 hours. If you send Voyager a command today, and it replies immediately, the reply arrives the day after tomorrow. And on the 18th of November of this year, 2026, Voyager 1 will reach a distance of 1 full light day from Earth, 25,902,068,356 kilometers, which is 173.14 astronomical units. 49 years of flight at 17 kilometers per second to put 1 day of light between itself and home, and the signal that crosses that gap is almost nothing. Voyager's transmitter runs at about 23 watts, comparable to a dim light bulb. By the time that transmission reaches Earth, spread out over a day of travel, the power arriving is on the order of a billionth of a watt. It is collected by 70-meter radio dishes at Goldstone in California, near Madrid and outside Canberra, and it is only detectable at all because we know exactly what frequency to listen on and exactly when. A dim bulb, 25 billion kilometers away, still being heard, and the delay makes every mistake enormously expensive. In the summer of 2023, a routine set of commands sent to Voyager 2 tilted its antenna a couple of degrees away from Earth. 2 degrees. At that distance, 2 degrees is enough to miss the planet entirely, and the spacecraft went silent. There was no possibility of a quick correction, because a correction would take the better part of a day to arrive, and another day to confirm, and the antenna was no longer pointing anywhere useful to receive it. The team eventually recovered it by transmitting the interplanetary equivalent of a shout, the highest powered command the network could produce, aimed at where the spacecraft should be, in the hope that enough of it would spill into a misaligned antenna to trigger a reset. It worked, weeks later. That is what troubleshooting looks like when the round trip is 2 days long. I want to name the thing this adds up to, because it is the part of the 4 that I find hardest to put down. Nobody has ever had a conversation across the solar system, and nobody ever will. Every command ever sent to a spacecraft beyond the moon has been written to a machine that has stopped existing in the state it was addressed to. By the time your instruction arrives at Jupiter, the spacecraft you were talking to is 35 minutes into a different situation, and its reply, when it comes back, describes a moment that is by then over an hour in the past. There is no now that the two of you share. There is only correspondence, a permanent exchange of letters between people who can never be in the same conversation. That is not a limitation of our technology, and it is not something a better antenna solves. It is what distance is, once distance gets large enough. The solar system is arranged so that its parts can only write to each other. Voyager 1 gave us the one image that holds all of this at once. On the 14th of February 1990, from about 6 billion kilometers out, it turned around and photographed the Earth, a single pale point less than a pixel across, caught in a band of scattered sunlight. That portrait crossed a delay of 5.5 hours to reach us, a picture of home arriving from the past. Before we finish, I want to deal briefly and honestly with something that circulates, because it deserves an answer rather than a dismissal. There are people who argue that these distances are unverifiable, that nobody has ever really measured how far away Mars is, that the figures are inherited convention, that the planets might be lights rather than places. The answer is that planetary distances are among the most redundantly measured quantities in all of science, confirmed by at least 5 completely independent methods. Radar ranging bounces a radio pulse off Venus and times how long the reflection takes to return. Campaigns in the early 1960s pinned the astronomical unit to a few parts per million, which is precisely why it could eventually be fixed by definition rather than measurement. Lunar laser ranging bounces light off reflectors left on the Moon by Apollo and by Soviet landers, and returns the Earth-Moon distance to centimetre precision. Spacecraft Doppler tracking measures the frequency shift of a moving transmitter, and it is accurate enough to deliver a lander to a target ellipse a few kilometres across after a 9-month cruise, which would be impossible if the distance model were wrong by even a small fraction of a percent. Cassini's radio science tested a prediction of general relativity to about 1 part in 100,000, using those same distances. And 2.5 centuries ago, the transit of Venus expeditions of 1761 and 1769 derived the scale of the solar system from parallax alone, telescopes, clocks, and sailing ships, and landed within a few percent of the modern figure. 5 methods, separated by 250 years, all agreeing. There is also a hoax worth mentioning, because it is instructive rather than threatening. Every August since the genuine record approach of 2003, a message circulates claiming Mars will appear as large as the full Moon. At that record approach, Mars was 55.7 million kilometres away and appeared as a point about 25 arc-seconds across. The Moon spans roughly 1800. For Mars to look like the Moon, it would have to be nearer than the Moon. The hoax survives because it exploits exactly the intuition this video has spent 2 hours dismantling, the assumption that close and close enough to see are the same idea. So there it is, all 4. And now I can answer the question I asked at the beginning. At the beginning of tonight, I asked you a question and promised I would not answer it until the end. The question was, how far away are the planets really? Here is the answer. There is no such thing as the distance to a planet. Not one distance. There are 4 of them, stacked on top of each other, and each one is worse than the one before it. The first distance is the number, and the number does not exist. There is no figure you can write down for how far Mars is from Earth, because the gap is a function of the date, and it swings from 54.6 million kilometres to 401 million, and back again, forever. The best you can offer is a range, and even the averages disagree with each other by 65 moon journeys, depending on which meaning of the word average you happen to reach for. And once the number is gone, the ranking goes with it, which is why the nearest planet to Earth is not Venus but Mercury, the nearest planet on average to every other planet in the solar system, sitting there in plain sight for 150 years, while everyone copied the wrong sum. The second distance is the path, and the path is not the gap. Nothing we have ever built has travelled to another world. Every one of them changed orbits instead, falling around the Sun along an arc that for a Mars trip runs about 10 times longer than the distance it closes. Cassini covered 3.5 billion kilometres, to reach an orbit 1.5 billion out, and spent its first 2 years flying toward Venus to do it. Messenger covered something like 8 billion kilometers to reach the house next door, and the path comes with a timetable, a door 2 to 4 weeks wide, opening once every 26 months, with no appeal available if you miss it. The third distance is the price, and the price is not measured in kilometers at all. It is measured in kilometers per second, and when you convert the solar system into that unit, the whole map rearranges. Mercury, the nearest planet to everything, costs about 13 kilometers per second to orbit. Mars, nearly 4 times further out, costs under 6. Closer became more expensive, and the reason is that the Sun sits at the bottom of a funnel, and falling inward is free while stopping is not. And the fourth distance is time, and this is the one that actually answers the question, because time is the only unit in which any human being has ever experienced a journey. 5 years to Jupiter, 6.7 to Saturn, 6.5 to Mercury, or 8 if you go the modern way. 9.5 to Pluto, at the fastest departure speed ever achieved, with a push from Jupiter. 12 years and 5 days to Neptune. It takes decades. That is the answer, not a number of kilometers, not a diagram. The honest reply to how far away the planets are is a span of years long enough to contain a career, and the reason the number under the picture felt harmless is precisely that it was a number. It was the wrong kind of object for the question, and it always has been. The diagram is not the distance. I said that in the first part, and I meant something small by it then. That the labels were mislabeled. I mean something larger now. No drawing can carry this. You could lay the solar system out perfectly to scale across 11 kilometers of dry lake bed, with the Sun as a beach ball and Neptune 2 kilometers away, and the drawing still would not tell you that Mercury is harder to reach than Saturn, or that the door to Mars opens for a fortnight every 26 months, or that a message to Neptune and back takes 8 hours, or that a person can give 50 years of their life to a single crossing and not live to see it finish. None of the 4 distances is a spatial property. Only the first one even pretends to be. And so we aim at where things will be. That is the discipline this whole subject teaches, and it applies at both ends of it. To the spacecraft, which is thrown once at a position its target has not reached yet, and to the people who commit their working lives to arrivals they may not attend. Now, let me put the other half of this down, because I do not want to leave you only with the size of it. We crossed it anyway. That is the fact I keep returning to, and it does not get said enough. Every planet in this solar system has been visited. All 8. Not observed from a distance. Visited, photographed from close range, weighed, measured, sampled where possible. A species that had not worked out how to fly at all in 1900 had, within 70 years, put people on the moon, and within 90 had touched every world in its own system. We did that with chemical rockets, slide rules, borrowed gravity, and an enormous amount of patience. The distances did not shrink. We simply agreed to take the time. Though I should be precise about who did the crossing because it matters. Every one of those visits was made by a machine. Only 24 human beings have ever travelled beyond low Earth orbit, all of them on Apollo missions, all of them between December of 1968 and December of 1972. A window of 4 years, more than half a century ago. Nobody has done it since. And the destination for all 24 was the Moon, which sits 1.28 light seconds away and can be reached in 3 days, and which is therefore the only place beyond this atmosphere that has ever been in conversational range of home. That is the honest shape of human presence in the solar system. We have sent our instruments everywhere and gone, ourselves, precisely 1 step, to the single destination near enough that the 4 distances almost do not apply. Everything further has been handled by proxy, by machines we could only write letters to because the 4 distances make the alternative, something no one has yet been willing to ask a person to do. And some of what we sent is still out there working. Voyager 2 reached Neptune 37 years ago, has been in flight for 49, and is still transmitting, a machine built with 1970s electronics, running on a slowly cooling lump of plutonium, 20 billion kilometers from the people who made it, most of whom are gone. Its twin will put a full day of light between itself and this planet in November of this year. They are the only objects we have ever sent that will outlast the species that sent them, and they got there at 17 kilometers per second, which is a speed you could not use to escape a parking ticket in astronomical terms, sustained without interruption for half a century. I said at the start that the answer was far worse than the number you were given, and I hope by now that has stopped sounding like a threat and started sounding like something else. Because worse, here, does not mean more hostile. The solar system is not arranged against us. The two enormous gaps that hold Uranus and Neptune at arm's length are not a barrier that was put there. They are the frozen record of a rearrangement that finished 4.5 billion years before anyone existed to be inconvenienced by it. And there are other systems out there, compact ones, where every world would be a few months away. Ours simply came out like this. The distance is not personal. It is just the shape of the house. But I will leave you with the thread that stays open, because it is the one that unsettles me most, and it is not about the size of anything. Uranus and Neptune have been visited exactly once. Once, in the entire history of our species, for a few hours each, in January of 1986 and August of 1989, by one spacecraft older than most of the people listening to this. There is nothing on its way to replace it. There has been nothing on its way for 37 years, and the reason is not that we have lost interest or the ability or the will. The reason is that the crossing takes longer than the institutions that would have to fund it can plan for, and longer than the people who would build it can expect to work. That is what the fourth distance actually costs. Not propellant, not money. It costs the outer half of our own solar system, held just far enough away that reaching it requires more continuity than a human society has yet managed to sustain. There is a version of this that is worth carrying with you, and it is smaller than all the numbers. The next time you see one of those diagrams, on a wall, in a book, on the side of a lunchbox, you will know 4 things about it that you did not know this morning. That the numbers underneath describe orbits rather than gaps. That the spacing has been compressed by a factor of thousands to fit the page. That the ordering by nearness is wrong, and the little grey one at the left-hand end is our closest neighbour. And that if you wanted to visit any of them, the correct question is not how far, but when would I be back? Everything you were shown as a child was true, and it was drawn on the wrong kind of paper, in the wrong kind of unit, in a shape that does not exist. And the real answer, the one that accounts for all 4, is far worse than the number you were given, and far more interesting. The planets are not somewhere over there. They are decades away.